Hello everyone, and thank you for joining us for the webinar today. My name is Ben Hutchins and I'm part of the marketing team here at Innovise. The webinar today will introduce how you can harness AI to optimize water distribution and supply networks using the power of InfoWorks WS Pro and Optimizer from Optomatics. As we move through the slides today, if you have any questions, please type them into the question box located in the right corner of your GoToWebinar interface. We have two experts to guide us through the webinar today. Firstly, a warm welcome to Lucy Pocock, Senior Optimization Engineer at Optomatics. After spending 3 years in the UK providing on-the-ground technical support to local utilities, Lucy is now based in Melbourne providing strategic support for customers in Australia, New Zealand and around the world. As a Senior Optimization Engineer in the strategic support team, Lucy works with utilities and their consulting partners on education, training, and the application of Optimizer to a range of clean and wastewater applications. She specializes in using Optimizer's functionality to inform growth planning, develop supporting procedures, and facilitate the implementation of resilience methodologies. Joining Lucy, we have Rebecca Wiley. Rebecca joined Innovise 2 years ago, having previously worked at Atkins. She is one of our solutions engineers and specializes in the water distribution product set. She helps provide technical information about the products and how you can fully utilize your software. I'll now hand you over to Rebecca to take things away. Over to you, Rebecca.
Thanks very much, Ben. Next slide, please. Thank you. So welcome everyone. I just wanted to start because we have people from all over the world of why we should and do care and why what we're going to talk about is really part of a bigger global picture. And so while the webinar today and in the upcoming series that I'll be doing does focus on how you can achieve different elements of project and utility work to meet your KPIs, ODIs, increased efficiency and decreased cost, it is important to stop sometimes and remember why. So I just wanted to highlight the 2030 Agenda for Sustainable Development, which has been adopted by all UN member states and provides a blueprint for the planet and for the people now and in the future. And at its heart are the 17 Sustainable Development Goals that you can see on the screen. And they recognise that ending poverty and other deprivations must go hand in hand with strategies that improve health, education and reducing inequality, while looking at climate change and the wider natural environment. Next slide, please, Lucy. And while the development agenda recognises that water is embedded in all forms of what we do and of development, in agriculture, in food security and health, Goal 6 ensures availability and sustainability of water and sanitation and is known as the Water Goal, which highlights a clear focus on this from both a social and economic prosperity point of view. The targets for the goal are here and can be found on the UN website. And today, as we talk about water supply and distribution networks, we focus on the ability to achieve universal access to safe and affordable drinking water for all. So water experts within our industry, a lot of you on the call would fall into that category, aim to plan, manage and operate the existing and new infrastructure that we have all over the world. These water systems and each individual asset and customer can be represented in a hydraulic model to help understand and drive investments for continuous improvement in resilience, ensuring water quality, managing the provisions of water sources, and ensuring a continuous supply of water for all. So to do this, the application we have at Innovise, InfoWorks WS Pro, brings in a whole range of third-party data sources together to accurately represent your water network, both existing and then new. InfoWorks WS Pro's standalone modelling platform, so independent of any GIS, SAP or telemetry platform, which means that range of data can be used to build a model and continue to update that automatically. The connection to telemetry databases enables you to view data such as flows, pressures, reservoir levels, water quality within WS Pro, which can aid with your calibration. So you can graph your model results with live data on the same graph to ensure you are achieving your parameters. Background mapping and geospatial connections to Google Maps and Google Street View enable you to make more informed decisions for planning and design. You're able to see if an asset is on a roundabout or outside a school and whether that needs additional consideration for your planning and operation. So sometimes when you're building or updating a model, maybe you're looking at proposed design or as-built information has not been received yet. A model can still be developed with the information you have. There are tools in the software for you to assess this information quickly, to find gaps and infer missing asset information from engineering judgment. For example, if you had missing height information, that could be gathered from nearby assets or a terrain model. The same for diameters. If you had missing diameters from as-builts, those could be inferred from surrounding pipes until you got more detailed information. Connectivity and network tracing allows the user to ensure that imported assets are connected to the network as quickly as possible and to trace downstream of treatment works or a district meter to allow you to see the network connection as well as that it has been imported correctly. Next slide, please, Lucy. The technology in InfoWorks WS Pro allows multiple people in a team to have access to the same model at the same time. So when you're doing that model build, you can have multiple people updating that model at the same time and checking that model. This centralizes the data, so the transferring of models between users, you get away from that, and enables your modeling community to have one version of the truth, to have one base model for their hydraulic information, where models can be updated, calibration changes can be incorporated back into a common base model. So when you need to do project work, you know what the latest, most accurate model is. The process of developing a model and accessing these results can then be really sped up with this process. It gets away from the admin kind of side of things, and a fully version tracked history keeps every asset and model change for you to see. So you can really see how a model has evolved from base data from GIS through to some updated information from a site survey to then your proposed design. Or you can see someone's changes that they have made prior to you picking up the model, so you have confidence in what you're working from. So hydraulic models can be built and used to examine a whole range of problems, and in the coming series we're going to be picking up a few of what you can see on the screen. And they can provide analysis and results for a range of solutions and problems to mitigate against customer quality and quantity. Looking at assessing resilience and to inform business plans, we have a tool to assess critical pipes, the availability of fire flow, and to monitor and manage leakage. Full water quality assessment, including the ability to look at chemical reactions between different solutes and substances, means that more informed decisions can be made about taste and odour when looking at source blending and operational changes that could affect the age of water and turbidity. The models can go down to a customer point assessment and for both hydraulic and water quality. And so this means when you're looking at your assessment for project work, you're able to see the effect on exact customers for exact lengths of time. And we, as I said, we will be exploring more of these in the coming sessions. So just finally, before we move on to Lucy and how we can take that planning hydraulic model and use it to optimize your investments. Just wanted to highlight that once you have this hydraulic model, WS Pro is an offline planning tool and can be used for to answer some of the questions that we had on the previous slide, so around growth, water quality and risk assessment. But at any time, this can be developed into an operational modelling tool for an operator to make live decisions about the network, linking in telemetry data and demand forecasting to look at the consequence of events, to mitigate the effects on customers. And again, this will be a whole other session that we will discuss later in the series. But now, Lucy, over to you.
Thanks very much, Rebecca, and thanks to Innovise for organising this. It's great to be here, getting a chance to introduce Optimizer and WS Pro. So I'm going to expand on what Rebecca talked about in highlighting some of the WS Pro functionality, and today I'm going to be talking about how we can harness artificial intelligence to optimise water distribution and supply networks. Now that's quite a mouthful, so we can break down a little bit some of the topics I'll be going over in the next half hour. So we're going to talk about how can optimization help me get more out of my hydraulic models? What kind of data is required to run an optimization? How does Optimizer work with the Innovise modeling software? Lost my clicker here. And what kinds of optimizations can be done with Optimizer? And finally, what are the potential benefits for me as a modeler or engineer and for my utility? So I'll be giving a pretty broad introduction of how these platforms can work together and how we can get more out of your WS Pro models by using Optimizer. So I'm going to start with a poll here. We've got a couple of poll questions at the start here, and these are aimed at reflecting on our current traditional planning process, so our business as usual approach. So I believe you can see a poll here. The first question we're going to ask is, are you currently evaluating your modelling options manually? So if you could take a moment here to answer that question. We've got a pretty overwhelming majority here saying yes, they do, which is great. So we're in the right place for today's webinar. So the second poll question now is, do you currently limit the options based on engineering judgment to make that analysis more manageable? So again, just a yes or no. We'll let a few of those answers come in. And again, we've got a pretty strong majority so far. We'll just let a few more votes come in. But we're at around over 80% saying yes, they do. And the final question in the poll here is just expanding on that. How many scenarios do you normally create for comparison? So we've got some ranges there to choose from. And we'll give people a few moments just to enter their answers there. So the most popular option is around the 2 to 3 or 4 to 5. And I think we'll give a few more minutes and then we might be able to show the results of that poll just to show the spread there. So yeah, I think we end up with about 40% looking at 2 or 3, 40% looking at 4 or 5, and a few looking at that more than 10. So pretty good spread, but most people looking more than 1, less than 5. So that is a bit of a reflection on, you know, the traditional planning process and how you may currently use your WS Pro models to make your engineering decisions. So now we're going to take a moment to think about how that process changes if we're using Optimizer with our hydraulic model. So let's consider that we're looking at growth in our network. So in my 30-year growth projection, I can see that my current network is not able to meet my required performance standards. And I can see that in my WS Pro model in terms of my minimum pressure requirement, and I've mapped my performance here along a y-axis. So we can think about performance with plotted them here as performance penalties. So poor performance, where we're currently operating, is quite high on this axis. And we want to get down to this acceptable level of performance. And the lower we go, the better our performance is. So tackling this problem in the traditional approach, as an engineer, I would sit down with the hydraulic model and use my engineering judgment and my network experience to test out different strategies of interventions and augmentations to try and solve that problem. So these are represented by these 5 points, where these are 5 different strategies that I've come up with that I think might help improve the performance in my 30-year growth scenario. So I evaluate these in terms of performance, and I can see that 2 still perform quite poorly, and I have 3 solutions that perform around my acceptable level. So I'm quite happy with these 3 solutions, and I'm going to take them forward for costing. I can see that this solution is cheaper than my other 2 solutions, so I'm going to discard the more expensive solutions and adopt this one. And as we saw in the polls, due to restraints in terms of time and just resources that I can spend on this project, I'm probably going to adopt this solution and take that forward for more detailed design. So now if we think about what this process looks like using Optimizer, instead of discretely testing out 5 different strategies, in Optimizer we're going to define everything that can possibly change in the network. So all the possible configurations that I could change. And on the other side of that, we're going to define all the required performance requirements that I want to meet in my network. And Optimizer is going to use its connection to high computational capacity clusters and its inbuilt algorithms to run through many thousands of combinations of those strategies. So this is great for 2 main reasons. One is a cost saving. So it's the most tangible output really. We generally see cost savings of around 20 to 30% when using Optimizer. And when you think about the sheer number of solutions Optimizer is able to test, we can see how we're able to arrive at that. It's not that the engineer didn't know the network well, it's just these are complicated systems, and Optimizer is able to find those pockets of optimal strategies that are cheaper and better performing than we can manually with our limited time and resources. So aside from the cost saving itself, the insight we get into our problem is another really great benefit. And we can see that summarized here in our green points. So this is our Pareto front of optimal solutions. So Optimizer doesn't just give us one solution or one strategy, it gives us a whole range of optimal strategies for a range of different costs. So this is really good because we can, as the engineer, we can start to ask much more interesting questions of our problem and take our analysis much further. So for example, if we didn't have a budget, I could ask, well, how much money does it make sense for me to spend on this problem? And for that, I'd want to look around the knee of the curve to see my most cost-effective solutions, where I'm getting the best value for money. Beyond that point, I can see the money I spend doesn't get me as much improvement in my performance. On the other side of that, if we have a limited budget, we know that we can get the best performing solution for our given budget. So it's that kind of confidence that we're able to apply to our decision making. So this was quite a high-level introduction to comparing the traditional and the Optimizer approach. So we're going to continue this discussion in a bit more detail. So breaking down Optimizer's framework and the parts that are core to the Optimizer technology and the parts that are configurable or that change from model to model. So first, it's the computational intelligence. So that's the back-end integration between the hydraulic model and the high computational cluster, enabling many more solutions to be run than you could do manually just running the model. The second is the algorithms. So this is something that's built into the Optimizer software. These algorithms, we've been working on them since we started as a company almost about 25 years ago. So these algorithms are very well trained to quickly and efficiently solve these kind of problems and come up with optimal strategies quickly. And finally, the graphical user interface. So I'll give you a brief overview of that in some later slides. But you'll see the interface makes it quite simple to define this optimization problem. In terms of the configurable inputs, this first one is obviously a really important part. So this is our model. So this is our WS Pro model that we need to bring in. So Optimizer is completely separate to the hydraulic model. We need that model defined in WS Pro. The second is the objectives. We'll talk about some examples of these, but we can think about what we're trying to optimize for. And thirdly, what the actual interventions and performance criteria are. These will obviously change from problem to problem. So again, just summarizing the value adds there with Optimizer, considering all the possibilities. So that's the connection to the computation, the ability to run your model many more times. The second is the algorithms, enabling you to consider multiple objectives at the same time, and they're very quick at solving these problems. And finally, acting with confidence. The outcomes that you get from Optimizer are data-driven solutions based on your model. We're not simplifying that model. And the outcome, as you can see with that Pareto, is giving you transparent information. So you're able to have really engaged discussions with your stakeholders around why you should be spending a certain amount of money or how much you want to invest for this particular problem. So just briefly here around our integrations with Innovise products. On the collection side, we integrate directly with InfoX ICM, and on the distribution side, obviously, with WS Pro. So taking a few moments here to walk through what the workflow is between working with WS Pro and Optimizer. We start by importing the InfoX database into Optimizer, and that's something that we've built with Innovise to directly connect into the database. So we can connect that through WS Pro Exchange. The second is formulating the optimization, and this happens in the Optimizer desktop software. The third step is running the hydraulic model and refining the formulation. So that's something that's just done locally on your machine. Then we're ready to submit for optimization, and that's done on a computational cluster. The fifth step is to open those optimization results, interrogate them, tweak as needed. There's likely some iteration through as you might want to refine the formulation. And at any time, we're able to export solutions back into WS Pro to view them with all the visualization functionality that WS Pro has. So you can push that strategy back in to view when you're ready to look at it. So this is a very simplified drawing of the architecture, but just to give you a bit of an idea of how it's set up. So as I mentioned, you have your local machine where you've got WS Pro and Optimizer. So they're working together as you're setting up the formulation, loading the model into Optimizer, running solutions manually. This can all happen on your local machine. This is enabled with WS Pro Exchange, which is how Optimizer can change things in the WS Pro model and also how it can get results back out from WS Pro to calculate the penalties and the costs. So through an API, when you're ready for optimization, the optimization itself is going to occur on a cluster where there's a bank of WS Pro solvers with WS Pro Exchange. So that's going to enable the many thousands of combinations of your model to be run, and then you're able to get that back onto your local machine for interrogation. So briefly here, I'm just going to touch on the Optimizer interface. I've got some screenshots here. So in the center, we have a map display where I would have my WS Pro model that I've imported. On the right, we have what we call our plan editor. So each column here represents 1 point from the Pareto chart. So I can see a summary of my costs and performance penalties, and below the line here, which is cut off, I could see my decision outcome, so what's been chosen for that particular strategy. Here's just another view. I can see an example of a Pareto which has been optimized, and I'm able to interrogate these results within this software. I'm also able to take any of these strategies into WS Pro. And then down the bottom, we just have a grid for viewing our network elements. So we have 5 steps we need to think about when formulating an optimization. The first step is, what is the question? What's the problem? This is an obvious one, but it is really important to define our problem statement up front and to really be clear on what are we optimizing here, what are our objectives. The second is our input data. So we need our hydraulic model, obviously, and cost data to support our options that we want to consider. There may be additional asset information we need to bring in to support that formulation. So we need to bring that input data together in Optimizer. The third step is where that engineering judgment really comes in. So Optimizer in no way replaces the need for experienced engineers who know the network to be solving these problems. We're just enabling the engineers to spend their time less on the iterative process of running and checking results and more able to spend their time on more interesting parts of the problem. So this is a step where the engineer is going to define the options, or what we call the decisions in Optimizer. And it's important to understand that Optimizer does not come up with strategies on its own. It's not going to invent a pipe where there is none. The engineer or the user needs to define all the potential strategies, so defining the range of interventions that could be considered, and then Optimizer is going to test out different combinations of those strategies. The fourth point is defining the design performance. So we call this the design criteria. And this is also where that engineering judgment comes in. We need to tell Optimizer, how do you want your model to perform? Where is that criteria most important? How do we want the hydraulics basically to perform at the end? And finally, what scenarios are relevant? So once we've set up the optimization and we've run the optimization, we may want to consider a slightly different growth projection, or what about climate sensitivity, or perhaps there's some cost sensitivity that we'd like to optimize on. So we can run the optimization on a number of different scenarios to take that analysis further. So here we have some examples of the Optimizer WS Pro functionality. This is by no means a complete list, but it shows some of the functionality we have built to date. In terms of the decisions, these are the things that we can change in the WS Pro model. So as expected, we have pipe sizes, valve settings, pump curves, reservoir volumes, and as well as capital decisions, we can also make control changes in the model. So we could change a UPC, we could change when a pump is turning on. So basically anything you're changing as part of trying out different strategies, any parameter in WS Pro could be a decision in Optimizer. In terms of the design criteria, these relate to the hydraulic outputs of WS Pro. So we're looking at pressure, velocities, reservoir levels. We can also look at things like water age or leakage. So this is any result from the model that you want to check. Some possible objectives, these are just some examples. For example, whole of life cost, adapting to growth, master planning, leakage, water quality. So there's a range of things we can optimize for. And the cost data, as expected, we need to bring in the cost information to support our various capital infrastructure upgrades. So we need to define how much our new pipes, for example, will cost. So now I'm going to take some time to walk through a case study. So this is a project for Southern Water in the UK. And here they were looking at optimizing their strategic grid. So this was looking at long-term integrated planning. In the south of England, in the Hampshire region, they're facing a projected deficit in an extreme drought condition in the future. So based on a number of factors, such as climate change, where rainfall is predicted to decrease in the future, population is predicted to grow, there's changes in regulatory requirements, so improved performance targets, improved efficiencies, sustainability reductions. All of these combine to predict a significant deficit in this system. On top of that, there are legacy issues from the aging of the existing infrastructure. So the optimizer question here was around meeting that deficit from a range of potential sources in the area, and as well as that, optimizing the infrastructure to supply that deficit across the region. If we take a moment to think about the complexity of this problem, there were 7 resource strategies that had been identified as potential ways that that deficit could be met. Along with that, there was obviously many asset options that could be used to distribute that new water around the network and integrate it with the existing system. So we have a range of resource strategies and a range of asset combinations within those. So the solution space is a pretty astronomically high number. It's quite a complex problem to solve. Tackling this manually would be very challenging to tackle with confidence. Southern Water were looking at what assets were required to provide regional resilience under those drought conditions. The interdependencies here meant that the grid needed to be optimised and designed as a single entity. So it played really well into an application for Optimizer. Translating that problem statement into the categories of how we break things down in Optimizer, we can think of the inputs as the WS Pro model, which had been built, the costs for the different capital infrastructure upgrades, and the supply-demand scenarios. So that was all developed before they came to using Optimizer. The decisions were the pipe alignment and sizing, storage location and sizing, pump sizing, and operational strategies. And the criteria was pressure, min and max flow, velocities, reservoir levels, and water age. So our criteria here, although quite simple, we can imagine these can get quite granular and detailed when we think about how they're actually applied in the network. Overall, we're looking to minimise cost and maximise level of service. So a detail here that I just want to highlight in terms of the scenarios, so this was a detail in the WS Pro model setup, actually considered 2 days worth of demand. So because this system needed to work across a severe drought, which was the worst case scenario, it also needed to function in an average day. So they wanted to look at the performance of different strategies across both of these scenarios. So in WS Pro, a 48-hour simulation was set up, and this was used as the hydraulic model, which was brought into Optimizer. So for Optimizer, whatever model is defined in WS Pro, we can bring into Optimizer. Taking a moment before we look at the results here, as we start to dive into the results, some of the focus questions we look at are, what are we building and where? So that's identifying the specific alternatives for the interventions. So we're really trying to focus and understand the size and location for the optimal assets. As well as that, we also want to understand the cost and performance measures. So we want to know why are these the best, most defensible decisions. So these are some of the questions that we keep in mind as we dive into the results. Here I have an example. This is a snapshot taken from one of our online dashboards. So we can see performance versus cost here. If you remember from the example problem at the start, we can imagine a horizontal line here defining acceptable performance. So the designers knew that although we do have a range of optimal strategies here, the strategies up here actually don't meet the required levels of performance. So these solutions highlighted in red were the feasible range of solutions. So these are the strategies that we can zoom into and focus on for analysis. And as an example here, these are some examples of what 3 different strategies could look like from that feasible range. You can see how the sizes of our assets change as we move along this curve. We spend more money and we continue to see performance improvements. So this slide is again looking at scenarios. So as I mentioned with the 48-hour run, all of these optimizations were being undertaken across the 48 hours. So every strategy was being tested in the drought as well as the average day. So the performance is a combination of both of those scenarios. Here I've overlaid two separate optimizations, one in green and one in blue. And these represent two distinct supply strategies. So as I mentioned, there were 7 different resource strategies that were identified as ways to meet that deficit. You can imagine within those different resource strategies, there is different asset combinations that give you the best cost and the best performance. So here we can see in green, one strategy, one resource strategy has been fixed and the assets within it optimized. And in blue, a different resource strategy has been chosen, and here the assets again are being optimized. So this is interesting in a problem such as this where we have different big picture decisions to be making. We can start to compare and contrast how these two resource strategies differ in terms of assets identified. So if we zoom in on this part of the curve, we can see how where they start to overlap. And behind each point here, we can start to identify common assets that have been defined as optimal across both strategies. So we can see similarities and differences here. So this is an example of that scenario analysis undertaken in Optimizer. So overall, this project is still ongoing. It is definitely not finished and there'll be more optimization to come. But so far, for the analysis to date, Southern Water have seen a 30% reduction in whole of life cost based on what they were potentially thinking needed to be built. And some of that saving has come from no-build solutions being identified from Optimizer. So as well as the actual outcomes, the insight and the ability to scale the optimization across different scenarios has been quite valuable here. So I'm going to wrap up that case study there and jump now to one more poll question for the presentation. So the question I want to focus on now is, do you account for social, environmental and or carbon impacts as part of the optioneering process? So thinking back to what we currently do and how we currently tackle our engineering problems, we've got some people, some answers coming through. We'll give people a couple more seconds. So we can see most people, the majority there with over 60%, are considering all of the above. The second is environmental with around 30% and a smaller number on carbon and social. But the majority are considering most of those. So you know obviously that these other factors are a very important part of the decision-making process. So in Optimizer so far, I've talked a lot about how OPEX and CAPEX can be optimized, as well as the hydraulic performance. But as you know, is necessary and integral to these decisions, we also need to be including other factors. And that can be challenging with the traditional process. It can be difficult to consider carbon and social benefit and environmental benefit as we're trying to optimize for hydraulic performance and cost. This is a very simplified plot, but just demonstrating how we can take Optimizer into 3 objectives. And so, for example, we can look at cost and performance, as I've talked about. And on our third objective, on our third axis, we can look at something like carbon, for example. This enables us to concurrently consider all of those objectives, and we're able to optimize against all 3 at once, rather than having to find the best hydraulic performing solution, then add the cost, and then add the carbon. So that brings me to the end of my presentation. I'm just going to give a quick summary here to tick off some of the key points. So as we've seen, Optimizer integrates directly with InfoWorks WS Pro. Optimization removes the grunt from the trial and error modelling approach. We're not removing the need for engineering judgment. We're not replacing engineers. It's just making that process more efficient. We're able to balance competing objectives to make unbiased and defensible decisions, which leads to a more holistic and cost-effective planning approach. As I mentioned, around 20 to 30% cost reduction on average across projects. So I think we actually do have one more poll question, which is, would you like further information? So we'll give people a few seconds to answer that, and then I'll hand back to Ben to wrap us up.
Excellent. Thanks very much, Lucy. Yeah, we'll just leave that poll question open for a few moments. But thank you very much, Lucy and Rebecca, for introducing us to the power of InfoWorks WS Pro and Optimizer today. If you asked a question, we promise to get in contact with an answer for you. I'll be updating you with a recording of this webinar next week and providing you with links to our upcoming webinars. Please do visit our website for more information about our virtual training courses, and please take a moment to complete the quick survey that follows this webinar to receive a certificate you can use for proof of professional development. Lastly, a big thank you for joining us today. We hope you have a great day, everyone.